So in this warm-up, we're doing the same airplane problem we've been doing with just slightly backwards. So what I saw a lot of people writing, which was really good, is normally we do airheading, like the airspeed plus the wind equals your ground speed, equals your ground resultant. Here, we're not given the airspeed, we're given the ground speed. So you kind of, instead of adding these two together, it's really ground speed minus wind equals airspeed. So you're subtracting instead of adding. However you chose to write it up. So there's my, the desired resultant vector. There's my wind. And I kind of wrote it out and I said, hey, look, we want some speed plus the wind to equal our final resultant. So our C, you're just subtracting. So I got the vector 216-ish and 380-ish. So what happened here?
Negative 45 right here, but you put a negative scale or something.
You like double negative.
You did a double negative. Yeah, yeah. Okay.
Why did I even write that negative down?
That's what happens. Okay. Because you actually did a triple. You did a triple negative. You have a minus, a minus, and a minus.
Negative.
Yeah.
I don't know why I wrote that negative sign
Yeah.
behind the 64.
Okay.
Just my,
So back there, you got the 216, and you, but the 289 is wrong.
Yeah, we just counted.
No.
Oh, okay.
Yeah, because we were subtracting. That makes sense.
Right. Okay. But it affected a lot. Yep. Yep. So you both kind of did the same mistake. You both did some double negatives. All right. So anyway, so I did my inverse tan, and I got an angle of around 60.4-ish, and then a speed of 437.4 miles per hour. All right. Good. Are there any questions on that? Okay. Let's move into today's lesson, which is it's the day 1 of lines and planes in space. So today we're doing lines in space. Tomorrow we're doing planes in space. And Friday we're doing lines and planes in space. Now on the calendar originally, tomorrow was supposed to be a quiz day. So tomorrow I wanted to give you guys a day off where we just focus on quizzes. I would have loved it, except we lost a day next week for the Accuplacer testing. So I had to scrap the quiz day because I can't pull out 2 days. So tomorrow we're just going to keep moving forward. We are going to starting to finish up the first quiz that you kind of started for a few minutes on paper the other day. So I have those hard copy if you want hard copies, and you can keep working on those and see if you can get those first quizzes done today after the lesson. All right, lines in space. Quick question before we do anything. What 2 things do you need for an equation of a line? Point and slope, right? You guys remember that from last year? And the last 5 years. Okay, point and slope. Point and slope. Same thing goes for vectors in space, except we don't call it slope anymore. We call it I call it a direction vector, which is what a lot of people call it. Most people call it a direction vector. So your slope, since slope normally is just a number and it's rise over run, and it gives you the ratio of how far up you need to move over how far over. Now, you can't just do a single number. It's not like you can do rise over run over run. It doesn't work, right? It's not a simple ratio. You got 3 numbers. So what do? You just keep it as a vector. And you say, hey, instead of just doing slope, rise over run, we're going to keep it as a vector and say, to get from one point on a line to another point on a line, I move this far to the x, this far to the y, this far to the z, and now I'm on the line again, right? So we call it our direction vector. All right, so because of that, we have to write equations of lines a little differently. So there are 2 ways that we write equations of lines in space. And both of these get used a lot, so you have to know both of them. So the first way is to write them parametrically. So you have your x component, your y component, your z component, and you just write each of them separately. So if you write your line in parametric form, then your x1, y1, z1, that's your point, and then your a, b, c, that's your direction vector. So it's very similar to equation of a line in like regular old-fashioned form, where you'd have like slope times x, you know, some slope times x plus some other point gives you your y or whatever. Now it's just kind of finagled a little bit. So anyway, x equals the x value of the point plus the x component of your direction vector times t. Right? And then you just do it, same thing for y, same thing for z. If you write the equations symmetrically, the nice thing about symmetric forms of the equations is you don't have that fourth variable in there. Here, you have x, y, z, and t. Here, you get rid of the t's. You just have x's, y's, and z's, and everything else is numeric. How do you write the symmetric equations? For me, what I do mentally, I know what they are, but personally, my brain still goes through the process. I always go to my parametric first, and then I just mentally solve each one for t. So t equals x minus x1 over a, it equals y minus y1 over b, it equals z minus z1 over c, right? And since t is the same, you know, it's one spot, right? Since t is the same for all three, you can set those three equal to each other. So those are called the symmetric equations of a line. So you have parametric equations and you have symmetric equations. You have to know both. But they're pretty simple. Both of them, all you need is a point on the line and a direction vector. All right, are we ready? Okay.
We're in symmetric.
By the way, to go backwards, so if you're going from symmetric to parametric, just set it equal to t, right? And then just solve for, like if I want to solve for z, so I get z equals ct plus z sub 1, right? So you go backwards. So set it equal to t and solve for the letter. Here, you solve for t. All right.
Sorry, I'm going as fast as I can.
That's okay. There we go. See? You're not alone. You're not alone. My shoe. All good? Okay. All right. So we're going to start with an example. Find both the parametric and symmetric equations of the line that passes through the point 1, negative 2, 4, and is parallel to vector v, 2, 4, negative 4. If it's parallel to that vector, what does that mean? Same direction vector. If you want, and you don't have to, but if you want, you could, instead of using 2, 4, negative 4, you could use direction vector 1, 2, negative 2. Because it's still the same direction vector, right? You just need it for direction. You don't care about the length. So you could, when you start seeing these direction vectors, if they start being kind of like big and hairy, if you can pull out a common multiple out of every term, feel free to do it. Because for a line, it's like saying having a slope of 6 over 3 versus 2 over 1. It's the same slope, right? It's just that one's not simplified, but they're still the same. So it's the same here. You can pull out a common multiple if you want to, but you don't have to. I don't think I did. I don't remember. Once you get your equations, then I want you to check with each other, make sure you match. Yeah, it's your direction vector.
One of two minus. So like there's 2, 4, negative 4, but you can simplify that to 1, 2, negative 2.
You were out yesterday.
But I didn't.
I'm sorry.
Or like adding. Adding was
Yeah, I don't even know why.
That's kind of scary.
Yeah. I'm not before my
Felt like you couldn't get enough in there.
yeah, I find not forgetting yeah.
I wonder if your lungs are kind of
And then
confused.
for symmetric.
I used to have that.
I for symmetric I got x minus 1 equals x plus 2 over 2 equals v minus 4 over negative 3.
Breathing's kind of
Yeah.
Oh, you did the simplify. Yeah. So
Did you
I
watch
got
the
x
screencast
minus
from
1 over
yesterday?
2, y
You got
plus
a
2
little
over
graphic.
4 equals v minus 4.
Well, if you need, like, the SmartBoard notes are there and the screencast is there.
It's like just solid multivariable.
And it's just cross products.
Yeah.
But we had to squish triple scalar product and parallel pipeds in like the last 10 seconds of the lesson. But it's there. Okay. So our parametric equations, remember your point, your point, x1, y1, z1, right? And then this is essentially like your slope, it's your direction vector. So 2, 4, negative 4. This is your A, B, C, right? Now, and so there's your 2, there's your 4, there's your negative 4, and then there's your point. So how, did you guys put the right numbers in the right spots? Yes, Dorsa. Absolutely. So if you have the equations x equals 1 plus t, y equals negative 2 plus 2t, z equals 4 minus 2t, exactly the same. Yes. Good. Any questions on that? Okay. So your symmetric, exact same thing, just written in symmetric form. Again, the 2, 4, negative 4 could be a 1, 2, negative 2. And so those are all just multipliers of time. So essentially, when you think parametrically, we're just doing an equation of a line. So if you have a different multiplier of time, t, like if t represented time, all it would mean to have a multiple of your direction vector is that you're moving along the line faster versus moving along the line slower, right? You're still on the same line and you're still generating it, just different values of t to create the same line. All right. So let's do it. I'll take it up a tiny notch. Find a set of parametric equations, so I just asked for the parametrics this time, that pass through the points negative 2, 1, 0, and 1, 3, 5. So now I have not given you a direction vector. I've just given you 2 points on the line, and you have to generate your own direction vector.
So are we supposed to use sometimes I just can't.
Yeah, it doesn't matter.
Is it okay?
I just want to share.
I thoroughly enjoy that little cartoon.
Yeah, it just has to be the vector. That you can use that.
All right. So I found a direction vector 3, 2, 5. Does that work? Could you have used -3, -2, -5?
Yeah.
Yes. Could you have used 6, 4, 10? Absolutely. Right? Any scalar multiple of the direction vector is fine, right? Okay. So how did I get the 3, 2, 5?
You turn the point minus the initial point.
Exactly. Yeah. You subtract your points to create your vector. All right. So those are my parametric equations. If I had used, I used the point -2, 1, 0. If I had used the point 1, 3, 5 for my point, would it have still been correct or would it be wrong? Still be correct, because it's still a point on the line times the direction vector, right, to generate the whole line. Good. So there's a lot of different answers. Are there any questions on this one? Hi, how are you doing? Yeah? Did you have a good night last night? Really? Can I ask what you did? Just homework? That was a good night? Okay. All right. Okay. So, can you do it backwards? Find the coordinates of a point P on the line and a vector V parallel to the line if I give you the line. I think you can do this.
I believe in this.
When do we start doing
Calculus? That's a fair question. Chapter 13. There's no calculus in chapter 12.
Oh, this is chapter 12. I
Yes.
was thinking chapter 1.
No, we're in
And I was
chapter
like,
12.
What do you mean?
We have 12 more units to go.
So our next test doesn't have any calculus on it?
Correct. This first test has no calculus. It's all just vectors.
And so our second test, will that be a chapter
When is
after
it?
this?
Yes, after this chapter, you have what you need to know in order to start doing all the calculus stuff. Yeah.
Is this next week?
It's the 23rd. It's a week from Monday.
Oh.
Oh, so
Okay.
All
All right, so, Michelle, what point did you get?
I got 0.54.
Did anyone else get 0.54? Just a couple of you? Okay. Oh, Jack, you got it? All right, good, good. Oh, yes, you're backing him up. You second the motion. All right, fantastic. So, Ian, what did you get for your direction vector? Not -4, 1, -3?
Oh,
Yeah,
no,
it's okay.
-4.
They're both correct. Yeah. I just said it. Okay. All right. Very good. Any questions on going backwards? Just pulling the information out. All right. We're almost done.
with the lesson?
Yeah.
Oh, wow.
It's a very short lesson. Yeah.
Wait, what
So-
do we do for the rest of the hour?
You're going to take quizzes.
Oh,
Yeah.
That's fun.
Can we just start with just start with tomorrow's lesson as well?
No. All right. Tomorrow's isn't that long either, then. We will. You know what? We could do
But
Bench
if
Up
we do
Wednesday.
tomorrow's lesson, then we can have a quiz day tomorrow.
Yeah.
Oh.
That's tempting, Miss Price.
No. Do it.
But you'd have 2 homework assignments.
And then we'd have done the next day.
All right, let's see. All right, we'll see how this goes. I don't know. I think doing lines, I know this is pretty simple, but then once we start adding planes to it, I don't know if that might be too much for one day. But anyway, all right, so because this question is actually like quite a big notch up, all right? So here's what we're going to do. We're going to determine whether these lines intersect, and if they do, we're going to find the point of intersection and the cosine of the angle of intersection for these 2 lines. So this is trickier than you think. All right. For 2 lines to intersect in space, the x, the y, and the z have to be the same, right? However, does the time that they hit that point on the line have to be the same? No. So you have a problem, right? Because, so the first thing you're going to want to do, this is kind of confusing. So the first thing I always do is I rewrite my lines parametrically. But you can't use t's for both because the time on one line is not the same as the time on another line. So you have to pick 2 different letters. I think I used, if I remember right, T and Q. A lot of books use subscripts like T sub 1, T sub 2, right, for time on the first line, time on the second line. But whatever you do, I personally would suggest you start by writing them in parametric form, but use different variables for your time. Those are my 2 cents. So now, in order for them to intersect, x does have to equal x, y has to equal y, and z has to equal z. And you end up with a lovely system of 3 equations and only 2 unknowns. So technically, you can just do 2 of these, but yeah, see what happens.
Oh, wait. Yeah. It's a different idea with the computation. You're so free. You just there's 3. That's what I don't know if it's right. Taking a leap of faith.
Oh, yes, yeah.
So, if you find T or Q, and then plug it in, you will change it. And then C, if there is value 2, 1, I got 1, and value 1, and 2, and then C, yeah. Work on the
You just
set them equal to each other.
like it's just
So you set the x equal to the x and the y equal to and then you simplify that a little bit.
So I got Q equals 1 and
Right.
T equals
negative 1.
okay.
Yeah.
Says Q.
So I set x equal to x and y.
I got Q equals 1 and T equals -1.
Then simplified that and then did a little bit. What did you get? Negative 1
What'd you get for Q?
I
I got Q equals 1 and T equals -1. I got Q equals 1 and T equals -1.
Oh wait, that's not the answer.
Good.
I feel you.
Good. And now you're to a number.
Oh, there's a 2.
Oh, I subtracted.
Yeah, Q is 1 and T equals -1.
I added the.
So I found Q.
You found Q?
Yeah.
Okay, so now plug the t back into the first equation and see what point you get.
Because 2 minus 3 is.
Oh, that's what you found. I don't know why I was stuck on that.
So we would get 2 possible intersections, right?
T is only t. T isn't like, t is t, so t has to go in for t. Q has to go in for q.
When we get 2 points.
So then.
Because if we plug in
Plug it in.
T to the top line,
Yeah,
then we would get like a point, right?
right?
And then if we plug in Q for the second line, we could get a different point.
That's the question. If you get the same point, then that means that's a point of intersection. That's what we're checking for. You should get the same point.
Wait, so it's okay if you get different.
T's and Q's. It's okay to get different T and Q's because that's just those are just time values of when you hit the point.
Oh.
It's just these systems of equations. So what I did was I used the information from like the thing to get like my point of vector, and then I used this stuff to like get my equations. I just did extra work. So I just like that.
Oh, good. Good. Okay. So now you're just finding
Plug
the
it
angle.
into. I think you plug it
I don't know
into
exactly.
So really all it is the angle between those two vectors. So you're just doing the direction
Or is
vector.
x, y, z a variable and not a point?
Yeah, they both give me the same point. So
It's your standard.
The point is
So we
x.
can-
Because I did
So your
not get the
vector
same
from your
point.
first
She
one
said
to
they have to be
negative
the same in order to
361,
be
and then the vector from the
Oh, I got
second
you
one
one.
to 4, and you
Or not substitution.
Remember, vectors don't have
Yeah,
Give them what you
Yeah,
got.
so you can
Don't
plug in
substitute.
the direction, you just guide
Add the
it.
16,
Guide it by the
negative
angle.
16. Wait, that's the X, that's the Y. Why is it Z1 just like that?
What's gonna be angle of intersection?
Yeah.
So
So
the
no, I'm trying to figure out what the.
Did you get negative 1?
So you have your formula.
And then you just plug it in.
Then you
Yeah.
plug it into these equations to get the.
Oh, right, the dot
Yeah.
But they didn't.
Oh,
the
yeah.
same number.
So I know, you've heard a lot. You've learned a lot, there's a lot of info in your head right now.
I think
They're
I
second point?
Wait.
Just solve it.
Oh yeah, yeah, yeah.
Solve it and it should give you the same.
And I didn't pause the recording, so it's been recording the whole time we've been sitting here with you. That's great. All right, so whoever's watching, I apologize that you've been sitting there staring at the same screen for 10 minutes. All right, so all I did was I let x equal x, y equal y, z equal z. You get 3 equations with 2 unknowns. You can pick any 2. You don't need 3 equations. You only need 2 of them, right? So you solve, and you end up with I solved, I got q equals 1. At q equals 1, we get the point 5, negative 4, 2 on the second equation. If you solve for t, you get t equals negative 1. Did you guys get those? Okay, so you plug that in for your t and see if you end up with the same point, 5, negative 4, 2. So if you get the same point on both lines, that means they intersect at that point. That's your point of intersection. Now to find the angle of intersection, that's just the angle between the two direction vectors for the line. Remember, if you have two lines, the direction vector for this guy and the direction vector for this guy, vectors don't have a location in space, right? They just have a direction. So you can orient those like wherever they are. You can just find the, like put them together like this and find the angle between the two. And that would be the same as the angle at the point of intersection between the two lines. So really the angle is just the angle between the two direction vectors. Da, 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 da. So there's my two direction vectors. Angle between two vectors is the dot product over the product of their magnitudes, right? So without simplifying, I got 4 over the square root of 966. Did you get that?
Huh?
I thought you said you got that. Did you get that?
No, I did not do that.
Oh.
Yeah.
Don't forget this formula because you're going to use this a lot. Angle between two vectors. It's just the cosine of the angle between two vectors is just their dot product or the product of their magnitudes. Yes, Jack?
To get the direction vectors, you just use the point from the equation.
I just looked at the original equation, right? Remember, negative 3, 6, 1, 2, 1, 4.
And then use the intersection point.
I didn't use the point at all. All you need are the direction vectors to find the angle between them. You don't need a point at all. You can, so if they don't intersect, you're just done because the angle between the two, so if you have two lines that don't intersect, say they're what's called skew, right? They're like this, like they never intersect. Then if you find the cosine of if you find the angle between their direction vectors, you are finding an angle, and it would be the angle like if you were looking at them head on, it would be that angle. But it doesn't really have a lot of
those values.
Good. Any other questions on this? All right. So I have a little review. Let's see for a minute how much we remember. So see if you can do this. Try to see if you can figure out most of it without looking at your notes. All right. So I've given you 3 points. So A, B, and C. Let's see if you can find the projection of vector AC onto vector AB. You're going to have to find the vectors, then find the projection. See if you remember the projection formula. The angle between two vectors. Find a vector orthogonal to two of those vectors. Find the parametric equations of AB. And find the symmetric equations of AC. Okay, so this is almost like a quiz in a review slide, right? So the first question, which I'm gathering from many of you, was the hardest, not like numerically taxing, but just you got to remember the formula for a projection, right? So first you got to find the vectors. So one of the things that I got fleshed out with a few different groups is that vector AC is not A minus C. Vector AC is C minus A, right? So make sure you're doing ending minus starting for your vectors, okay? All right, so when you do for the first one, so there's AB, there's AC, there's B. I must have just written them all just to have them handy, right? So the vector or the projection of AC onto AB is their dot product over AB squared times vector AB. What helps me remember this is the one on the bottom is the one on the bottom. Does that help? I mean, no? I mean, that helps me, right?
That's how I remember it.
Okay, all right. So the one on the bottom is the one on the bottom, right? Dot product is both of them, so it doesn't matter. So anyway, so yeah, the projection of AC onto AB is the dot product over the bottom's magnitude squared times this vector. It's a scalar multiple of this vector because you want to be in that vector's direction. So anyway, so that's what I got with a bunch of 19s. So you could pull the 19 out if you want. But are there any questions on the projection? Okay. All right. The angle between the two vectors, we just talked about that. It's the dot product over the product of their magnitudes, and then you have to do, that's the cosine, then you have to do an inverse cosine. Did I do an inverse cosine? I did. Look at that. So around 30-ish degrees. How'd you do with that one? Yes. Got it wrong? Are you sure?
Yeah, I got it.
Okay. Okay. All right. Good. Okay. The vector orthogonal. What are you gonna have to do for that one, Ryan? Cross product, right? Orthogonal is another word for what? Perpendicular. Yes. Okay. So you do the cross product. Back then, I was still doing diagonals, and I'm never gonna change these. I just don't have time. But the answer is 27 negative 110. Whoa.
See, I thought I had the scalar multiplier or something, but then I realized that 14 and 10 is wrong. So like I did this entirely wrong.
No. You have negative 27 and you have 1. So you're only off by your last one. So you have 2 minus 12, which is negative 10, right? You just added them. It's not a big deal. That wasn't like, it's not like you did the process was wrong. There's a difference between a process error and just a little calculation error, right? It's not a big deal. Good. Yeah.
So if you did the cross product of BA times BC, you get negative 7, 1, negative 10. That'd still be correct.
Yeah. The difference is that one's going to be pointing this way and one's going to be pointing that way. Yeah. All right. Let's see. Parametric equations. So parametric equations of AB. So you needed the point. So you could use either A or B, right? And then the direction vector for AB. Okay. And then symmetric equations of AC, same thing. You point either A or C and then the direction vector. How are we feeling?
Great.
Feeling great. All right. Good. All right. So that's it. We still have 6 whole minutes
Oh, wow.
That's a lot.
Next lesson.
for